In this video, we're going to look at transformations of functions. So let's just recall the library of functions. Sometimes these are called our parent functions. That's what I typically refer to them as. And we use properties of the parent functions along with identified transformations to graph other functions in this family. So if I know what a particular parent function looks like, if I have another function that I know lives in that family, then I know it's going to have similar characteristics. So this is a pretty common library of function that we have listed here, but there are some other parent functions that are not listed here. Those include our exponential functions, y equals a to the x, logarithmic functions, y equals log base b of x, and all 6 of the trigonometric functions that we learned earlier this semester. Our main parent functions in the library of functions, we have our identity function, y equals x, which is the parent function for all linear equations. Our squaring function, y equals x squared, which is the parent function for our quadratic functions. The square root function, y equals the square root of x, the parent function for all square root functions. Cubing function, y equals x cubed, parent function for all cubic functions. Cube root function, or the y equals the cube root of x. This is the parent function for all cube root functions. Reciprocal function, y equals 1 over x. This is the parent function for our reciprocal functions. I don't want to generalize too much compared to rational functions. We will look at rational functions a little bit more closely in another video. And then absolute value functions, y equals the absolute value of x. This is the parent function for all of our absolute value functions. Let's review some transformations. We have really 4 types of transformations. Or 3 types of transformations. We have shifts, reflections, and stretches and compressions. Our vertical shifts are illustrated in an equation by adding or subtracting a constant to that function. If we add a constant of b, f of x plus b, this is shifting the graph up b units. If we have y equals f of x minus b, this is going to shift the graph down b units. Horizontal shifts are illustrated by adding or subtracting a constant to the input of a function. So if we have y equals f of x plus d, this shifts to the left d units. And if we have y equals f of x minus d, this is going to shift the graph to the right d units. Now, the horizontal shifts, we do want to pay extra close attention to these rules. Those directions don't match intuitively to the sign of those. So just be very cautious with that. Reflections are indicated by a negative. So either multiplying the function value or the output by y, or the input, I'm sorry, by -1, or multiplying the input by -1. So y equals negative f of x, that's going to reflect about the x-axis, or I like to think about it visually as like a vertical reflection, so flipping up and down. And then y equals f of negative x. Again, I like to think of that as a horizontal reflection, which would reflect over the y-axis. A vertical stretch or compression. A lot of times these two are separated as 2 rules. I keep them as one, simply to minimize how much we have to memorize and how much we have to know. A vertical stretch or compression is illustrated by a scalar multiple on the output. Okay, so a times f of x. Now, this is going to vertically stretch or compress your function by a factor of a. Knowing the magnitude of a tells whether it's a stretch or a compression. But if we're graphing this, we're going to end up creating ordered pairs, and the way that we create the ordered pairs is the same whether it's a stretch or a compression. So that's why I group these together. In order to find the coordinates of your new function, you're going to take all the y coordinates and multiply them by a. So if a is small enough, you're going to see a compression. If a is large enough, you're going to see a stretch. But I just don't feel like it's necessary to break that down any further. As long as you know how to apply that transformation, ultimately you'll see it happen. You'll see whether it was a stretch or compression once you graph it. Likewise, with horizontal stretches and compression, this is multiplying your input by some constant. In this case, we're going to call it c. So we're looking at the equation y equals f of c times x. Now, whether this is a stretch or compression, again, not necessary for you to know until you can see the graph. But in order to apply that, what you're going to do is divide the x coordinates of your function by c, and this should say f of x. I realize there's a little bit of a typo here. So you're going to divide your x coordinates of f of x by that coefficient c. So let's practice. We're going to just identify the parent function and the transformations from the parent function, and we're just going to sketch. When you get into calculus, sometimes it's just so helpful to have an idea of what the graph of a function looks like. It's not always necessary that we have the perfect graph, but just a visual, an idea of what that's going to look like. So that's why we're going to just emphasize sketching the graph for these examples. So our first function f of x is x squared plus 6. Our parent function is going to be y equals x squared. So it's that quadratic. The transformations we have, that plus 6 is going to be a vertical shift up. So my parent function y equals x squared, that's our standard parabola with a vertex at the origin. Our function is going to take that graph and just shift it up 6 units. Since I have 2 graphs on my grid, I definitely want to make sure I label them. Primarily our function f of x, because that's what we're actually being asked to graph. That purple graph of our parent function is really just to help us visually see where we need to move to graph f of x. F of x equals -1 times the absolute value of x plus 5. So our parent function is y equals the absolute value of x. Now, this particular function has 2 transformations. There's that 5 inside of the absolute value bars, and there's that -1 out front. So the 5 inside of the absolute value bars shifts this left 5 units. And then that -1 is multiplying our output, that absolute value, by -1. So it's actually going to result in a negative reflection. So it's going to reflect over the x-axis. So when I graph, I'm going to start by sketching the graph of absolute value of x. That's our graph that looks just like a V. I'm going to graph both these transformations individually. You can choose to graph them all at once. For me, it's easier to process this one at a time. So I'm going to first start by going to the left 5. And then I'm going to take that resulting graph and I'm going to reflect it about the x-axis to illustrate my graph of f of x. Again, making sure I label f of x since there are some additional graphs on this grid. F of x equals the cube root of x minus 4. So our parent function is y equals the cube root of x. And our transformations at -4 or -4 on the inside of that radical, that's going to be a horizontal shift to the right 4 units. So my cube root function, kind of that flatter S curve, and I'm just going to take these and shift it to the right 4 units. There's my graph of f of x. f of x equals the absolute value of x minus 4 plus 3. Our parent function is y equals the absolute value of x. Our transformations inside the absolute value bars at minus 4 shifts it to the right 4 units. And then the plus 3 outside of the absolute value shifts it up 3 units. So again, starting with my absolute value graph, that nice V, I'm going to do both of these transformations in one just because the horizontal and vertical shifts I can put together at one time. But similar to our example B, you could do one at a time, just like we did there. So I'm going to go to the right 4 and up 3. And there's my graph of f of x. It should be a little bit off of that. I'm going to fix that one branch. They're not, those branches are not touching. All right, let's go back to our trigonometric functions. F of x equals sine of 3x plus pi. So obviously these transformations are the same. They are essentially representing those different transformations we talked at the beginning, are shifts, horizontal and vertical shifts, our stretches and compressions, and our reflections. But we think about them a little bit differently in terms of a trigonometric function. So we're going to sort of shift our language a little bit here. We're given f of x equals sine of 3x plus pi. Our parent function is going to be y equals sine of x. And then our transformations are going to be a change in the period. And we can also tell that we've got a phase shift here. So our period is going to be 2 pi divided by that coefficient on x, or 2 pi over 3. And then our phase shift, what we're going to do is set that argument equal to 0. So we're going to do 3x plus pi equals 0. 3x equals negative pi. X is equal to negative pi over 3. And when we were graphing these in a previous video, we really thought of this more as, where are we going to start our sine curve? So we're going to start that sine curve at negative pi over 3. So I'm going to start dividing my horizontal axis. I'm going to actually go by segments of pi over 6. So this is going to be negative pi over 3. And that makes this positive pi over 3. Our sine function, that parent function of sine, remember, it starts at the midline, goes up to the maximum, back down to the midline, down to the minimum, back up to the midline. So we take our period, which is in this example, 2 pi over 3. So if I start at negative pi over 3 and go to pi over 3, that's going to be 2 pi over 3. And now I've divided this up nicely into 4 segments as well. So I'm starting at my midline at negative pi over 3. I go to my max, which is going to be 1. I'm going to spread this out just a little bit so that I don't feel like I'm too compressed. So I'm going to set that as 1 and negative 1. So up to my max, back to my midline, down to my min, back to my midline. And so unlike those other examples where we graphed the parent function on our axis and then graphed the transformations of our function, with trigonometric functions, it's much easier to avoid that, especially when we start dealing with changes in our period. All right, and one more. F of x equals -1 times 3 to the x plus 2. Notice how I read this. It's -1 times 3 to the x. This is not -3 raised to a power of x. If we wanted it to be treated as -3 raised to a power of x, we actually would need parentheses around that -3. So I just want to emphasize that. So this is, I guess, we could be more clear, which we don't typically write it this way, but we could write this as negative times the quantity 3 to the x plus 2 by adding the parentheses around 3 to the x. So our parent function, this is an exponential, and it's going to be an exponential of base 3, so it's going to be 3 to the x. And then our transformations, where this negative out front is going to be a reflection about the x-axis. And then the plus 2 at the end is going to be a vertical shift up 2 units. Now, for this particular example, we don't necessarily have a visual of y equals 3 to the x. We are going to have a video later in this unit on exponential functions, but we can just make a quick table of values to visualize what our parent function looks like. When I'm creating these tables of values for parent functions, I like to make sure I label things very carefully because we don't want to confuse this table of values with our function that we're actually trying to graph of f of x. So x and y equals 3 to the x are my column headings. I'm just going to plot 3 points, -1, 0, and 1 for x. 3 to the -1 power is 1/3. 3 to the 0 power is 1. 3 to the first power is 3. So I'm going to sketch this graph, and I'm going to actually give myself a little bit more space going. Here's -3, +3. Just giving myself a little bit more space. It'll make it easier for me to plot these points. So I've got a point at -1, 1/3. I've got a point at 0, 1. And a point at 1, 3. So my parent function looks like this. So what I'm going to do with this particular graph is I'm going to first reflect it about the x-axis, and I'm going to do these individually. So if I reflect it about the x-axis, we get a graph that looks like this, and then we're going to just shift all these up to so my function is going to look like this.